Hey, welcome to The Explainer. Today, we're going to hunt down a ghost in the machine, a kind of technological glitch that can literally cost fortunes in the blink of an eye.
So, picture this. It's May 2012. It's the day of Facebook's massive IPO. The whole world is watching. But behind the scenes? Absolute chaos. A glitch in Nasdaq's system just goes haywire. It led to total confusion. Orders were changing and canceling randomly, and traders lost a fortune.
And we're not talking about a small hiccup here. This was one of the biggest IPOs in US history, a multi-billion-dollar event completely thrown into disarray by a single, tiny software bug. And it left everybody asking the same exact question. How on earth could something like this even happen?
So what was going on? Well, the answer lies in this really strange but surprisingly common problem that happens when bits of computer code, and I mean this literally, start to race each other.
And that story is our perfect starting point. A multi-billion-dollar glitch. The day computing chaos cost an absolute fortune.
Which brings us right to the heart of it, the race to chaos. Here, we're going to unpack the exact bug that was behind this whole disaster. Okay, so here it is. The villain of our whole story is something called a race condition. Now, what is that? It's basically a flaw where the final outcome of a program completely depends on the unpredictable timing of different operations. Think of it like this. Two or more tasks are racing to use the same thing at the same time. And the result? Well, it's usually just a mess.
I know, that probably sounds a little abstract. So let's break it down with a really simple analogy. Imagine two ATMs, right? And they're both trying to deposit $10 into the very same bank account at the exact same instant. What could possibly go wrong? All right, so here's how it's supposed to work, in a perfect world. ATM A goes first. It reads the balance, which is 0, it adds $10 and writes the new balance, $10. Easy. Then ATM B does the exact same thing. It reads the balance, now 10, adds its $10 and writes the final correct balance of $20. Simple, one after the other and totally accurate.
But in a race condition, things get messy. The instructions get all tangled up. So check this out. Both ATMs read the balance at the same time when it's still 0. Then they both add $10 in their own little memory banks. ATM A writes $10 to the account, and then, like a millisecond later, ATM B also writes $10 to the account. Poof! One of the deposits just vanished into thin air. The final balance is just plain wrong.
And believe me, it can get so much worse than that. When programmers ran a real test with 1,000 transactions that were designed to cancel each other out, plus 10, minus 10, that kind of thing, the race condition produced a final balance of $380 when it should have been 0. The code was literally creating money out of thin air, or sometimes losing it completely at random. And this isn't just about money. Imagine this bug in an airline booking system. You could sell the same exact seat to two different people. Yikes.
Okay, so how in the world do we fix this? How do we stop the race? Well, it's time for Taming the Code, where we're going to introduce a little bit of order to all this chaos.
So programmers use this powerful concept called synchronization to control who gets to access these shared resources. The whole goal is to protect what's known as the critical section. And that's just a fancy term for that specific chunk of code, like the part that updates the bank balance, that absolutely cannot be run by two tasks at the same time.
And the first tool we have for this is just beautifully simple. I want you to think of it as a do not disturb sign, but for your code. This tool is called a mutex, which is actually short for mutual exclusion. And yeah, it acts just like a do not disturb sign on a hotel room door. Before a task enters that critical section of code, it puts up the sign. And while that sign is up, no other task is allowed in, not until the first one is finished and takes the sign down. The whole process is this really simple three-step dance. First, a task acquires the lock. That's like hanging the sign on the door. Second, it executes its code safely, all by itself. And third, it releases the lock, taking the sign down so the next task waiting in line can finally have its turn. So, what's the result of all this? Let's go back to our bank account example. With the mutex protecting that deposit and withdrawal code, the race is completely eliminated. Every single time that test is run, the final balance is exactly what it should be, 0. Boom. Order is restored.
But, what if one at a time is just too restrictive? What if you need to manage a small crowd, not just a single person? Well, that brings us to our next tool for the job.
And this is where something called a semaphore comes in. The comparison is actually pretty simple.
A mutex is strictly one at a time, no exceptions. A semaphore, on the other hand, is for a few at a time. It lets a specific number of tasks access a resource all at once.
You know, the best way to really get this is with the parking garage analogy. A semaphore is kind of like the attendant at a parking garage that has a limited number of spots. Its whole job is just to keep account of how many spots are free.
So, let's imagine our garage opens for the day. The semaphore's counter says there are 3 spots available. The first car pulls up.
It gets a spot, and the attendant, our little semaphore, ticks the counter down. Now there are just 2 spots left. The next car arrives, same deal.
And then, the third car pulls in and takes the very last spot. The counter hits 0. Now, when the next car shows up, the attendant tells them, "Sorry, garage full," and that car has to wait. It's completely blocked until one of the first 3 cars leaves, freeing up its spot and letting the semaphore tick its counter back up to 1.
So why does any of this really matter? Because this isn't just about code, right? It's about maintaining order in a parallel world. From the massive database systems that run our banks to the apps on your phone, there are countless processes, all running at the exact same time. And managing them correctly is, well, it's everything.
So, at the end of the day, we've seen how programmers contain this chaos inside a computer. But it kind of leaves us with a bigger question, doesn't it? In a world that runs more and more on these parallel processes, where else is this hidden race to chaos affecting our lives? And what kinds of locks or do not disturb signs do we need to put in place out there in the real world?